afternoon, not after lunch session. This is a very special session. We have the Test of Time Award. We have the 2 Gems of Pot talks. And for the Test of Time Award, remember this is a paper that was published in 2008 and which is considered the most influential from POTS in that year. And this paper is the Chase Revisited. The award to this paper will be given tomorrow in the award lunch, right, together with Sigmund. So, Alin.
Hi everyone, can you hear me? Too loudly actually. I'm Alin Deutsch. We used to joke together with my co-authors for this paper that there must be something wrong with the way we're writing about the chase if, having such a catchy title, we keep missing out on scoring an Amazon bestseller hit. However, I'm sure I talk also in the name when I say that we'll take this award over an Amazon hit any day. I'd like to thank the award selection committee, the community for its nice feedback, and also in particular to my advisor Val Tannen, who taught me how to chase, in particular database queries, but also more generally career goals and dreams. I would like to dedicate the award to the memory of both of my co-authors, who are no longer with us, sadly. Jeff Remmel was a professor of mathematics at UCSD, a brilliant combinatorist who applied his techniques to computational complexity. As a matter of fact, he was the co-founder of the field of computational complexity for mathematical structures with Nerode. He was also a beloved and well-respected instructor and an extremely generous mentor and collaborator. And as for Alan Nash, he was a Renaissance caliber, multi-talented genius who, without ever having gone to college and received an undergraduate degree, was extremely successful in a variety of professions, ranging from CEO and founder of startups to assistant VP of Merrill Lynch to holder of 2 doctoral degrees, one in math and one in computer science from UCSD, to researcher at IBM Almaden, and finally founder of a computer trading hedge fund. I miss them both a lot, today more than usual. And their absence turns this event into a bittersweet one. So, talking about the sweet part, that of course is the chase, which you all know is a tool that is simply an algorithm that starts from a relational instance I and modifies it step by step as long as a set of given constraints sigma is violated. What is remarkable about this little algorithm is that it has been successfully applied to solve a variety of key database problems, ranging from query containment under constraints to certain answer computation, constraint implication, and data exchange, of course, the topic of the next Gems of Pots talk. For the remaining of this talk, I'd like to refer to all of these collectively as the motivating problems, because they motivated the study that we undertook in this paper. And in particular, we started from the question, is there any reason why this seemingly disparate set of problems admits the same algorithm as a solution? Is there any algorithm-independent reason for it? And we observed that yes, this is not accidental. Namely, we don't really care how the chase result is computed. What we only care about in terms of solving the motivating problems are a bunch of key properties that they satisfy. And we introduced the notion of universal models, which are models satisfying such properties, and then showed that what all these problems have in common is that to solve them, it suffices to exhibit a universal model. And the chase is just one algorithm for finding such models, not necessarily the best, not necessarily the only one. So, what do I mean by universal model? More formally, we're given an instance, a relational instance I, a set of constraints. Think of them at this point as just first-order logic sentences. For specific results, we limited the classes of constraints. And we say that a finite instance U is a universal model for I and sigma if there exists a homomorphism from I into U, which we denote with this arrow in the appropriate direction, and in which case we say that U is a model for I. Also, we require U to satisfy all the constraints in sigma, and then we say it's a model for sigma in the standard logic sense. And finally, we require for every model of I and sigma to have a homomorphic mapping from U into this model, in which case we say that U is universal. And I'm showing you here, let me first point out that for the purpose of the problems that we have in mind, we allow the active domain of both the initial instance and U to contain constants and variables. And until I say otherwise towards the end of the talk, universality is unrestricted, referring to both finite and infinite models. This is how we were denoting the universal model for instance I and set of constraints sigma. It's a notation I will not use anywhere in the talk. I'm introducing against all the presets of clear presentations, just as a nod to Alin, who was extremely passionate about notation, to the point of stubbornness, and who would usually engage his co-authors into long, protracted notation wars, which I miss today. Okay, so let's look at an example of a universal model for a very simple schema that has just one binary relation, which I'm going to interpret as the edge relation in a graph for the purpose of illustration. And we have here three constraints, which happen to be all tuple-generating dependencies, TGDs, where conforming to convention, the free variables are considered universally quantified. And if you look at the first one, it simply states that there exists a cycle involving two nodes, x and y, with an edge from x to y and one from y to x. The second constraint says that if such a cycle exists, then in the instance there has to also exist a self-loop around some node u. And finally, the third one says that for every edge from some node x to y, there is in parallel with it a path of length 2 going through an intermediate vertex w. Now, if our instance is the empty instance, just to simplify matters, then a universal model is, for example, the single node graph that has a self-loop. It's rather easy to see that it satisfies all the three TGDs. In particular, the second one requires the existence of such a self-loop. The first one can simply go around the self-loop twice in order to find the two-node cycle, because nothing in here states that the two nodes and the edges must be distinct. And similarly, the third one can use as interpretations for x, w, and y the same node u. It's also easy to see that this is a universal model, simply because according to the first constraint, any other model must contain such a two-node cycle, or at most two-node cycle. And then because of the second constraint, any other model must contain a self-loop which can serve as the image of the homomorphic mapping from the universal model. Okay? So, now that we have an idea of what universal models are, our observation was that what we really seek to solve these problems are universal models and not necessarily chase results. And the reason for the wide applicability of the chase can be formally given now under the following result. Given an instance I and the set sigma of TGDs, as well as EGDs, which are another famous class of constraints in which the conclusions of the implications you've seen before contain only equalities, then if the chase terminates, it yields a universal model. So based on this observation, we embarked in this paper on a study that decouples the algorithm, namely the chase, from the result, namely the universal model, and asks the fundamental question, how adequate is the chase for finding universal models? And in settling this question, we had to answer a list of naturally arising questions, such as, is chase termination decidable? Could there be universal models even when the chase does not terminate? Are there other algorithms that will find them? Can we handle larger query and constraint classes than the usual conjunctive queries and TGDs and DGDs that were represented in the typical solutions to the motivating problems? Let's start with a crash course in the standard chase for the same running example that we've seen, in which basically constraint is violated by the instance if its premise is, if the instance is a model for its premise but not for its conclusion, and firing a chase step with that constraint involves essentially bringing in facts that correspond to the conclusion, the missing conclusion of the constraint. So here, for example, if our original instance is empty, then of course the premises of the second and third constraints cannot be satisfied. However, the third one has a trivial premise, true, and a chase step with it applies, and its result is to bring into the instance a two-node loop. Once we've done so, the two edges will enable chase steps with the other constraints, because the second one, for example, requires now that there is a two-node loop, there should also be a one-node loop. And applying a chase step with it means bringing this loop in. Similarly, the two black edges that we've just introduced have no two-edge path in parallel with them, thus they violate the third constraint, and chase steps with the third constraint apply now. For example, bringing such a path in through a node W, and similarly for the edge from Y to X through a node Z, and so on. It should be obvious that the chase in this case does not terminate, because the yellow and green edges that we're introducing keep violating the third constraint. They have no path of length 2 in parallel with them, and we can repeatedly apply chase steps, bringing in these paths, such as here, and then here, and then here, etc., ad infinitum. So this brings us to the problem of chase termination, which, in order to state, we had to refine, taking into account the fact that in the standard chase, it can happen that several constraints are violated, several steps apply, and the one that is really fired is chosen non-deterministically. And therefore, it's possible for the same input instance and set of constraints for some chase sequences to terminate and others to not terminate. Which is why we asked the decision problem in its two flavors, settling it negatively in both cases. Is there some terminating chase sequence, or do all chase sequences terminate when the set of constraints is just a set of TGDs? And then we switched our attention to finding universal models, where our result in the paper plus prior results that introduced classes of constraints for which the chase was guaranteed to terminate, implied that there are universal models in those cases. For example, for the famous class of weak cyclic constraint that I'm sure you'll hear about soon. We asked, what about arbitrary sets of TGDs and DGDs? And it turned out that it's undecidable whether a decision procedure exists for checking the existence of a universal model. And with that hope dashed, the next best hope was completeness, We asked, is there a complete procedure for finding universal models? And that would be one that guarantees that it terminates and yields one such model whenever one exists, otherwise it diverges. And the natural first candidate, of course, was the standard chase. But we had bad news here, which is that the standard chase is incomplete, and the counterexample for its completeness is precisely the running example we have seen, in which, remember, that the self loop is a universal model for our constraints, and yet the standard chase diverges. The good news is that there exists a complete chase variant, which we call the core chase, and which, just like the standard chase, performs a sequence of steps, in which, however, every step has two phases. In the first phase, it applies all the standard chase steps that would have applied in the standard chasing procedure simultaneously. And in a second phase, it just computes the core of the resulting instance. So it minimizes it, finds the smallest substructure into which the instance maps homomorphically. Here's an example on our running example, starting again with the empty instance. Remember that the first chase step is with the first constraint, which brings in our two-node loop. And then when we try to compute the core, nothing happens because cycles don't map homomorphically on any substructure thereof. But then in the second step, remember from the previous result, there were 3 applicable chase steps, which for now we fire simultaneously, bringing in all those edges you've seen. And then we compute the core, and for that just notice that all the green, black, and yellow edges map into the red self-loop. This is the core, this is the chase result. The chase terminates now because all the constraints are satisfied, and this is the desired universal model. And this is not accidental. We prove in the paper that there exists a universal model if and only if the core chase terminates and yields it. And the corollary that is independent of the notion of universal model is simply that whenever the standard chase terminates, so does the core chase. And we know that the converse is not true. And this corollary is also true for any other chase variation that yields universal models, and to the best of our knowledge, these were virtually all of them known at the time. This is actually one of the results that has appealed to many chase aficionados, even if they didn't particularly care about the universal models. But we did. So for us, the study went further and paints the following picture, in which I'm going to distinguish between finite and unrestricted universality by introducing the notion of weak universal model, which assures only homomorphisms into the finite models of I and sigma. And to distinguish from them, we talk about strong universal models, which is what we have been talking about so far throughout the talk. So we know that the class of strong universal models is a strict subclass of that of weak models. We know that existence is undecidable, but the core chase is complete for strong models. We know that existence is undecidable, but there is no complete procedure for finding weak models, and therefore the only hope would be incomplete procedures. However, these cannot be chase-like. There are many more results in the paper. I will not detail them. I'll just summarize and wrap up with that. So we looked at the list of classical database problems and showed that they could be solved by exhibiting a universal model, and that the standard chase was only an imperfect tool for finding such models. And therefore, by separating the algorithm for the result, we improved the algorithm, coming up with a complete and most likely to terminate among all chase-like algorithms. And finally, we pushed the boundaries of the cases in which we can solve these motivating problems to beyond the case when a universal model exists. Sometimes there is no such thing. However, there is a finite set of models, of finite models, that are universal in the sense that for every model of the constraints, there is a homomorphism from one member of this set. And we showed that exhibiting such a finite universal model set was actually sufficient for solving all the motivating problems. And then we went one step further, parameterizing universality by the class of mappings used. In the whole talk, I've been talking about homomorphism homomorphic mappings, but we looked also at injective and surjective and embeddings, which were needed to solve richer classes of constraints and queries. So let me stop here and thank you all for your attention and put up again the two authors who really deserve any applause for this work.
There is a classical line of research in model theory that looked at different syntax, universal theories, existential theories, Horn theories, and try to look at their properties and characterize them, what are the preservation properties, and have a tight connection between these two.
Right.
So have you guys tried to look at how this is essentially, in some sense, this is a flavor of a model theoretic result. Have you tried to see how it relates to classical result in model theory?
Well, not directly as such, but we did take as inspiration the closure of the various formulae under certain kinds of mappings, and that is what we use to extend these results.
Thank you.
Okay, so let's